Good day to you. This is teacher Leland, Alejandro, and we're going to study today modeling with exponential and logarithmic equations. This will involve worded problems. So this is modeling with exponential and logarithmic equations. So we shall see the problems in the other side. So this will be for this particular lesson. Okay, let us start from the first number, and let's see the total first. Let's see the total first. So this will be about 8 questions. All right, 8 questions. So let us start with the first one. Okay, here's number 1. The half-life of a radioactive substance is the time it takes for half of the material to decay. Phosphorus 32 is used to study a plant's use of fertilizer. It has a half-life of 14.3 days. Write the exponential decay function for a 50 milligram sample. Find the amount of phosphorus 32 remaining after 84 days. So let us write the given first. So we have here a phosphorus 32 and half-life of 14.3 days. So let that be our H. So this is 14.3. This will be in days there. Write the exponential decay function for a 50 milligram sample. So that is the initial amount. Let's use A, and this is 50 mg, 50 milligram. Find the amount of phosphorus 32 remaining after 84 days. So we have this given time. This is 84 days. So units are consistent. Both are in days. All right, let's use the formula. Amount remaining P, function of time P, all right, equivalent to A times the quantity 1/2 raised to the exponent T over H. There. Here's the formula. Now, we're asked to write the exponential decay function, okay, for a 50 milligram sample. So direct substitution, this will remain P, and A becomes 50, that's the initial amount, times the quantity 1/2. Our variable is time over a constant half-life of 14.3. There, okay, so this must be, of course, 1. This is 14.3. There, all right. This is the required exponential decay function. All right, and so that's for the first question. Let's have the other question. Find the amount of phosphorus 32 remaining after 84 days. Okay, so we'll just use the 84 days in place of T to solve for the remaining amount after 84 days. So this will be P of 84. This will be 50 times the quantity 1/2 raised to 84 over 14.3. So this will be 50. Let's compute that 1/2 raised to the fraction 84 over 14.3. So that's 0.5 raised to 84, 14.3. That should be about 0.017, 04951, 046. And that's the equivalent of 1/2 raised to the fraction 84 over 14.3. Now let's multiply that by 50. We have the answer at 0.85. So this is after 84 days, we have 0.85247552228. And this will be milligrams. And we can round this to the nearest 100. This is 0.85 milligrams. All right, this goes to our first number. Let's see it from the computer. Okay. All right, so this is the required exponential decay function. All right. And this is the required remaining amount at 0.85 milligrams. So looks correct. All right, so that goes to our first number. Let's continue with the second. Here's the second. Archaeologists use carbon-14, which has a half-life of 5,730 years, to determine the age of artifacts in carbon dating. Write the exponential decay function for a 24 milligram sample. How much carbon-14 remains after 30 millennia? That's 31,000 years. Okay. All right. So we will use the same formula. Let's use the, let's have the given first. Half-life is 5,730 years. There. All right. Our initial amount is 24 milligram. That goes to our A. So this is 24 milligram. Okay. How much carbon-14 remains after 30 millennia? So that's time. This is equivalent to 30,000 years. So this time we're dealing with the years. All right, so the same formula. Okay, this function of time, amount remaining, is equivalent to the initial amount times 1/2 raised to time over half-life there. And so we have the amount remaining is equal to, let's use the A, 24. This is times 1/2 raised to time over half-life of 5,730 there. So this is 5,000 there. All right, 5,730. This must be the required exponential decay function. All right, let us solve the required. How much carbon-14 remains after 30,000 years? So direct substitution using this formula. So this is now P. This is now P of T. All right, is equal to 24 times 1/2 raised to 30,000 over 5,730. All right, let's compute. This will be 24 times the quantity, what is 1/2 raised to that fraction. All right, that's 0.5 raised to the fraction 30,000 divided by 5,730. Okay, we have something like 0.026541. 57705, and we shall multiply this quantity by the 24, and we have something like P at 30,000 is equal to 0.63699784992, and this will be in milligrams. All right, this will now be rounded to the nearest 100. This is only 0.64 milligram. There. Okay, this goes to our number 2. Let's check and verify. So these are the answers. This is the required exponential decay function. This is the remaining amount at 0.64 milligram. Okay, that will be our number 2. Let's proceed to number 3. Let's proceed to our third. Let's clear the screen. This is number 3. Okay. In May 22nd, 1960, the Valdivia earthquake in southern Chile is to date the most powerful earthquake ever recorded in Earth's history at 9.5 on the Richter scale. That's 9.5. Now, for earthquakes, we will have the formula magnitude. Okay, and this will be magnitude is equal to logarithm of intensity of the earthquake over I of 0. I of 0 is the smallest seismic activity, which is set to 1. Okay, so I of 0 is 1. So our working equation here will be reduced to m equal to log I, because I over I of 0, that's I over I1. So that becomes log I. So we shall use it with the Valdivia earthquake. So this will be mv is equal to log IV. And so our magnitude here is 9.5. So this is 9.5 equals log IV. Now this is base 10, okay? This is base 10. That means if we write this in exponential form, this will be 10 raised to 9.5, which gives the IV. So using the exponential form, IV is just 10 raised to 9.5. There, okay? So that gives us the intensity of the earthquake in Valdivia. All right, let's now have the next. We have for the second part of the problem. In March 27, 1964, the Alaskan earthquake occurred that had a magnitude of 9.2, and the shaking lasted for 4 minutes. How many times more intense was the Valdivia earthquake than the Alaskan earthquake? Let's compute first for the intensity of the Alaskan earthquake. We can now use MA. This will be for Alaskan. Okay, Alaskan. All right, this will now be MA is equal to log IA. There, log IA. All right, this will now be 9.2, which is equal to log IA. And then using the exponential form, IA is equal to 10 raised to 9.2. There. Now we can solve for the requirement now. How many times more intense was the Valdivia earthquake than the Alaskan earthquake? So we shall use a number k when multiplied by the Alaskan earthquake intensity gives the intensity of the Valdivia earthquake. So we shall use k. So let k be the numerical factor. Okay, just let k be the number. All right, so there. And so the equation is the Valdivia earthquake intensity IV is equal to k times the Alaskan intensity earthquake. Okay, there. All right. So this will be IV is equal to k times IA. So direct substitution, let us use IV is equal to k times IA. If we solve for k here, if we solve for k, k is equal to IV over IA. There. And so by using the numbers that we have, IV is 10 raised to 9.5 divided by IA, which is 10 raised to 9.2, which gives us 10. 9.5 minus 9.2. We subtract the exponents. We have something like 0.3. There. So 10 raised to 0.3, we have k is equivalent to How much is 10 raised to 0.3? That should be about 1.995262.315. And we can round this to 2, and that's the required number. So it's 2 times, okay? It's 2 times more intense. All right, so that will be for our answer, and the computer's answer is over here. All right, that goes to our number 3. Let's continue with number 4. Let's clear the screen and continue with the 4th question. Let's have the 4th. Okay, let's have the problem. In December 26, 2004, the Indian Ocean earthquake occurred with 9.1 magnitude, measured in the Richter scale. All right, so we have another earthquake here. We'll just call it Indian Ocean earthquake. And we will use magnitude. MI stands for Indian. This is log II over IO. All right, again, IO is the smallest seismic activity set to 1. So our equation is reduced to MI is equal to log II. There, because I sub 0 is 1. Now, direct substitution, our given is 9.1 magnitude. That goes to our MI. So that is 9.1 is equal to log II. Again, this is base 10. We can solve for II just doing the exponential form. 10 raised to 9.1 is II. So we have here II is equivalent to 10 raised to 9.1. And there we have the intensity of the Indian Ocean earthquake. All right, let's continue with the second statement. In March 28, 2005, a major earthquake occurred off the west coast of northern Sumatra, Indonesia, with a magnitude of 8.6 in the Richter scale. So this is for Sumatra. Let's just put the word Sumatra there. And we have the same formula, only this is now MS. And this is logarithm of the ratio IS over I of 0. Again, I of 0 is the lowest, smallest seismic activity set to 1. This equation reduced to MS equals log IS. And we shall now use our magnitude for Sumatra earthquake, which is 8.6. And is equal to log IS. And by using the exponential form, IS is found 10 raised to 8.6. There. And so let's have the final statement. By what approximate factor was the intensity of the Indian Ocean earthquake greater than the intensity of the Sumatra earthquake? Of course, we know the larger is the Indian Ocean earthquake. So if we multiply the Sumatra, which is the smaller earthquake, by some number greater than 1, okay, that will give the value for the intensity of the Indian Ocean earthquake. So our working equation will be, we shall choose a variable k, let k be the number, and this k will be multiplied by the smaller to get the larger. There. And so solving for k, it's II divided by IS. There. II divided by IS is the required number. So II is 10 raised to 9.1 divided by IS, 10 raised to 8.6. There. And this is equivalent to 10. That's 9.1 minus 8.6. That should be 0.5 there. And so K is the same as square root of 10, which is 3.16227766. Or rounded to the nearest 100, that is simply K is equal to 3.16 there. And this is the required number, 3.16, okay? 3.16 times the Sumatra earthquake intensity gives the larger Indian Ocean earthquake II. All right, so it's 3.16, okay? So that will be the multiplying factor. All right, so what's the answer from the computer? It's 3.16 greater, 3.16 times greater there. All right, so this will be our answer for number 4. Let's proceed to number 5. Let me clear the screen for number 4. Continue with number 5. Okay, here's number 5. This time it's sound level. Okay, this is something to do with sound level and loudness. All right, so in June of 1996, while the English house electronica band Left Field the group was playing at Brixton Academy, the sound system produced volume reaching 137 decibels. So this is decibels, this will be loudness. So let's use the left field first. So this is for the left field. And we have 137 decibels. This will be loudness, okay? So the formula for loudness is equal to 10 times the logarithm of the ratio, sound intensity over the smallest non-audible sound, okay? That's IO. So the smallest non-audible sound, okay, non-audible, okay, cannot be heard by the human ear. This is 10 to the negative 12 watts per square meter. There, okay, that's IO. And so we have here the loudness for the left field is 137 dB. So this is 137. Let's use the data. 137 is equal to 10 times logarithm of the ratio I. Let's call this IL over 10 to the negative 12. There. So if we divide both sides by 10, the 137 becomes 13.7. And this is equivalent to logarithm of the ratio IL divided by 10 negative 12. Okay, so taking the anti-logarithm of both sides, okay, taking the anti-logarithm, so we will have 10 raised to 13.7. This will be 10 raised to 13.7. And then you have like 10 raised to the logarithm of that quotient, all right? We will have just the fraction. IL is equals to 10 to the negative 12, okay? This will be just IL over 10 negative 12, okay? Like that. Remember, if you have something like 10 raised to the logarithm of IL over 10 to the negative 12 there, remember, this is base 10 here, okay? So this cancels out there. And you will have this as the answer. That's why you have it there. All right, so that explains it. Okay, we have taken the anti-logarithm of both sides. Okay, so let's continue with the IL. Let me clear that particular part. Okay, so solving for IL now. Solving for IL, this will have a continuation Okay, this will now be just IL is the product of 10 raised to 13.7 times 10 negative 12 there. So that 13.7 will be combined with the negative 12. So it's just 13.7 minus 12. It's like this. So you will have 7 and then this will be just 1.7. Okay. All right. So this will now be just 1.7 and the resulting IL is equal to 10 raised to 1.7 there. Okay. So that ends for the left field. Now let's have the second statement. In 2008, the Manowar band registered a sound pressure level of 139 decibels during the sound check at the Magic Circle Fest. So we have the second band named Manowar, okay? These are the bands with the loudest sound. There. Okay, this time we still have the same formula. L is equal to 10 log. This is I, let's call this IM, okay? And divided by I of 0, the same quantity over here, okay? All right, so this will be the loudness for the second band Manowar, and this is 139 decibels. 139, and here you have 10 times log IM stands for Manowar, and this is 10 to the negative 12. Okay, so after dividing by 10 both sides, you will have 13.9 here, and this will be equal to the same 10 times the logarithm of IM over 10 to the negative 12. Okay, after which, when we solve this, taking the anti-logarithm of both sides, we will have 10 raised to 13.9. And this will be equal to, of course, we have, this will now, let me clear this 10 here. When 139 becomes 13.9, let me clear the 10 there. This will no longer be here. There, okay. And so this will now be taking the antilog of this. This will now be like IM over 10 to the negative 12 there. Okay. Now let's clear the right side for some more writings. Okay. And so solving for the intensity for the Manowar, this will now be the product of 10 raised to 13.9 and 10 raised to negative 12. And so that will just be 13.9 minus 12. So we have the exponent first, 13.9 minus the 12 there. And we shall have here 9 and we have 1.9 there, okay? Yes, 1.9. And so the value of IM is 10 raised to 1.9, okay? So this will now be IM is equal to 10 raised to 1.9. And we have the two values, okay? And we have the two values. What we need is this and this to compute for the required, okay? All right, so let us have the third statement. What fraction of the sound intensity of the Manowar band was the sound intensity of the left field group? Okay. What fraction of the sound intensity of the Manowar band? The Manowar band is the larger. Okay. A fraction is some number between some number greater than 0 and not more than 1. Okay. It's a fraction. All right. Okay. So we will have to find that fraction and then multiply it by the larger to get the smaller left field sound level, okay? All right, and so let that number be K, all right? Let's use K. All right, so let K be the number or be the fraction, okay? Let that be the fraction. All right, so we shall relate this K times the larger Manowar band, and that will be for IL. K times IL is equal to, all right, we have the larger, which is the Manowar band, okay? So the smaller is the IL, okay? So the IL must be at the left, and this must be the one at the right, okay? Let me clear that. This will now be the larger IM there, okay? So our equation here is IL is equal to K times IM, or K, solving for K. This will be equivalent to IL over IM. The smaller divided by the larger, okay, to get the fraction. And so this will be equivalent to get IL, that's 10 raised to 1.7 divided by 10 raised to 1.9. And so this is equivalent to 10, and this will be like, how much is that? 9 minus 7, that's a negative 0.2. Negative 0.2 there, okay? So this is 10 raised to negative 0.2. So what's the value of 10 raised to negative 0.2? Let's compute that. Raised to negative 0.2, that should be about 0.63. Okay, so K is 0.63. Let's just put it at the right side over here. K is 0.63 there. All right, that's the only space remaining. Okay, so from the left side, this is 10 raised to negative 0.2. Let me clear that part. Okay, this is negative 0.2 there. Okay, all right, that's equivalent to 0.63. I wonder if it will fit here. There. Okay. All right, that's 0.63. That's the fraction, all right, the required fraction. So multiplying the larger by this amount gets the smaller, okay? All right, and so let us verify the answer. Let's verify the answer. Okay, over here. You can find it over here. 0.63. K is equal to 0.63. All right, at least we are correct there. All right. Such a long solution, all right? Okay, so let's do number 6. Let's do number 6. Okay, let's continue with number 6 here. This is something about chemistry, all right? The equation for the pH of a substance is pH is equal to negative logarithm of H plus, the concentration of hydrogen ions. A basic solution of hydrogen sulfide has a pH of 4.1. Lemon juice has a pH of 2. What is the approximate difference in the concentration of hydrogen ions between the two solutions? So we have the formula there, okay? We have the formula pH is equal to negative logarithm of the concentration of hydrogen ions, H plus there. All right, a basic solution of hydrogen sulfide has a pH of 4.1. So this is for hydrogen sulfide. That's 4.1, and that goes here. 4.1 is equal to negative logarithm of concentration of hydrogen ions there. All right, so what we have is the pH, dividing this by the negative 1, okay? Dividing this by negative 1 makes the right side positive. So we divide both sides by negative 1, Okay, the right side becomes positive logarithm of h plus there. And of course, the left side is now negative 4.1. Now, this is a common logarithm base 10. So taking the exponential form, remember there's a base 10 here, okay? All right, there's a base 10 there. Only we don't write that anymore. But taking the exponential form, this means the concentration of hydrogen ions, H plus, is equal to 10 raised to negative 4.1 there, okay? And that goes for the hydrogen sulfide there. Okay, let us now make use of the second. Lemon juice has a pH of 2, okay? So we use the same formula, all right? We make use of the same formula, pH, all right, is equal to negative log of the hydrogen concentration. All right, and this is now 2 for the lemon juice. This is negative log, the same H plus there. We divide both sides by negative 1. And left side is negative 2. Right side is positive logarithm of the hydrogen concentration. All right, so this will now be like that. And again, this is base 10. Converting this to exponential form, H plus here will be 10 to the negative 2 there. All right, what is the question? What's the approximate difference? What's the approximate difference in the concentration of hydrogen ions between the two solutions? So all we need to do is subtract, okay? We're after the difference. So we're after the difference. So let's call this D, and we shall get the larger minus the smaller. This must be the larger, okay? Because it is less negative in exponent, okay? So that means 10 to the negative 2 minus 10 to the negative 4.1 there. And we shall get the difference, how much? This will now be 10 raised to negative 2 minus 10 raised to negative 4.1. And we get something like 9.92, 0567, 177 times 10 to the negative 3 there. This is our answer, okay? Or we can round this to the nearest 100 for the significant digit, 9.92 times 10 to the negative 3 there, okay? All right, that should be our answer. Okay, 9.92 times 10 to the negative 3. Let's check and verify. Okay, over here, the computer's answer is over there. 9.92 times 10 to the negative 3. Let's continue with the next number 7. Let me clear the screen. Okay, here's number 7. Let's read. The equation for the pH of a substance is pH equals negative logarithm of the concentration of hydrogen ions. Okay, what is the approximate pH of a solution whose hydrogen ion concentration is 6.30957 times 10 to the negative 6? So what do we have this time? We have the H plus, okay? We have the H plus and we're looking for the pH. All right, and so we can start the solution. Our given, we have the H plus at 6.30957 times 10 to the negative 6. All right. What is the approximate pH? All right, so this is our formula. pH is equal to negative logarithm of the H plus. And so this is equal to negative logarithm of 6.30957 times 10 to the negative 6. There. Okay, so we just use our scientific calculator to get the logarithm. So negative of that logarithm will be 6.30957 exponent negative 6. All right, what we have is 5.2. This is 5.200. That's 5 zeros followed by 237. Okay, we can just round this to 5.2. This is our approximate pH there. All right, so that should be for our number 7. Verify the answer over here. There. So that's 5.2 and we're correct. Where? Let's continue with number 7. Number 8 now. Yes, number 8. Let me clear the screen. Here's number 8. All right, the general equation for depreciation is given by y is equal to a times the quantity 1 minus r, the entire quantity times, that's times a raised to t, okay? So it's 1 minus r raised to t times the initial or original cost, okay? So y is equal to the original cost times the quantity 1 minus r raised to t, okay? All right, so where y is equal to current value. So A is the original cost, R is the rate of depreciation, and T is equal to time in years. So the formula is given here. So we have Y is equal to the initial cost A times the quantity 1 minus the rate of depreciation R raised to time in years. The question is, determine the approximate current value of the car after 17 years. So the original amount A is in dollars, 26,675. There. All right. Now, after 17 years, that will be our time. So this will be 17 years. Okay. That'll be 17 years. And then the rate of depreciation, yes, rate of depreciation is 12.63%, or in decimals this will be 0.1263. There, that's the R. All right, we have all this. We can compute for Y, the approximate current value. All right, so direct substitution, this will be 26,675 times the quantity 1 minus, let's use the decimals, 0.1263 raised to the power 17 years. There. And so we shall compute. This will now be 26675. Let's compute for the value, the right side, 1 minus 0.1263. So that's 1 minus 0.1263 raised to 17. And this is 0.1007302025. Okay, we multiply this by the initial amount or the initial cost of the car. So times 26675. All right, this is it. This is in dollars. This is 2,686.978152. All right, and rounded to the nearest dollar, this will be 2,687. There. All right, so that's it for our number 8. Let's check and verify the answer. So the value of the car now is 2,687. That is 17 years after it was acquired. Okay, so that's it. That's the final amount. So you see how it depreciates from brand new. Okay, after using it for hundreds of miles, all right, the car becomes depreciated to a lower amount of 2,687. All right, so that's it. I think this is the last number. Okay, I think this is the last number, and I hope you were able to learn from our examples. And see you later for other worded problems. So this will be all for now. God bless, and I hope you score in your quizzes.